how many rectangles are there on in a chessboard. So this whole square is itself rectangle. Any small square is a rectangle, and of course anything like this is a rectangle. Um, and so we are trying to find out how many different unique rectangles will there be. So when you start off with this problem, a major problem is that a chessboard is an 8 by 8 board, and that's pretty big. So working with it could be a little hard. So what we can do is we can start with smaller numbers and we can look for patterns. So if we have a 1 by 1 square, right, there's just one rectangle, that's the only square. Let's look at if we have 2 by 2s. So this thing, well, there are, if you look at how many 1 by 1s there are 4 of those. And then we can look how many 2 by 1s there will be 2 of those. Similarly, if we look at 1 by 2s, there will be 2 of those. And of course there will be 1 2 by 2. This would be equal to 9. Let us also look at 3 by 3s now. So of course there will be 3 1 by 1s, and then we can look at 2 by 1s. So like this, and then thrice of those, so 6. And similarly 1 by 2s will also be 6. If you look at 2 by 2s, that is a square like this, it will be 4 of those. And then we can look at 2 by 3s. 2 by 3s would be 2 of those. And of course 3 by 2s will also be 2. And then 3 by 3 will be 1. Sorry, there will be 9 1 by 1s. Oh, and I forgot 1 by 3s and 3 by 1s. 3 of those, 3 of those. This will turn out to be 36. You can go over to 4 by 4s, but if we look at the current patterns that we have, as in n equals 1, 2 and 3, we have 1, 9 and 36. We can notice that these are actually 1 squared, 3 squared and 6 squared. And so we can see that this would be like 1 squared, and then 1 plus 2 squared, and then 1 plus 1 plus 2 plus 3 squared, and so on. Another thing that we might deduce from this is that if we want to go from n equals 1 to 2, we are adding 8. From 2 to 3, we are adding 27. So this could basically be 1 cubed, 1 cube plus 2 cube, 1 cube plus 2 cube plus 3 cube, and so on. And actually both of these are really the same, because the sum of natural numbers from r equals 1 to n is basically n plus 1 over 2. And if you want to square them, it would be this. And the sum of the cubes is also actually the same formula. That is easy to prove by induction. Right, so we can go ahead and try to prove this. So we can claim that for any n by n square, total number of rectangles is the same as the sum of natural numbers from 1 to n, and then you square it. In other words, it would be n plus 1 over 2 n squared. Right, so what we can do is, okay, so let's say there's a 3 by 3, right, and we can basically track how many 1 2 3s and 1 2 3s there are, and hopefully we can see some sort of a pattern. Right, so one thing to notice would be that this chart would be actually symmetrical, as in whatever is the stuff over here would be the stuff over here too, because since it's a square, the total number of m by n's is the same as the total number of n by n's. Right, so let's do the easy ones first. 1 by 1, there's of course 9 of those. If you look at 3 by 3, there's just 1 of those. 3 by 2 would be 2 of those, and 3 by 1 would be 1 of those. Right, simply because this is your whole 3 by 3. So if you have 3 by 2s, you can split it up like this and then like this. and then if it's 3 by 1 you can further split it up like this. Right, so from this sort of procedure we can see that if we have a 3 by 3, if we have n numbers of 3 by 3, then there will be twice number of 3 by 2. So if we have a 3 by 3, let's say this is 3 by 3, every 3 by 3 can be split up into two 3 by 2s. This would be one of them, and then this would be another one of them. So for every 3 by 3 there are twice 3 by 2s. So there are there's 2 of 3 by 2s. And so by very similar logic we can notice a similar algorithm that if there are n number of 3 by 2s, there will be twice the number for 2 by 2s, because every 3 by 2 can be split up into two of 2 by 2s, one that will be this and another one that will be this. So we can continue on and say that this will be 4 and then this will be 6, because if we have any 3 by 2, then we can split this up into 3 of 2 by 1s, one like this, one like this. Here's your 1 2 3. So we can see that this would basically be the multiples of 2, 4, 6, 8, all the way, right? And when you continue on the same algorithm to 1 by 3s, it would be 3, and this would be 1 2 1 2 3, right? And so what we can see is for any n by n, here's your 1 2 3 all the way to n 2 3 2 3 all the way to n, and then this would be the multiples of 2, that is 2 times 2 2 times 3 all the way to 2 times n. This would be the same for 3, and then this would be the same for n, and so on. This should be 3 of those. Sorry. This should be 3, and then 3 times 2 is 6, and so on. So what we can see is that we have 1 plus 2 plus 3 all the way to n, and then just this, and then you do the same thing but you multiply it by 2, and then you do the same thing, you multiply it by 3, and you continue this all the way till you have n, and you're multiplying it with the same number, right? So we can group these into 1 plus 2 plus 3 all the way to n, and then you multiply it with 1 plus 2 plus 3 plus all the way to n. In other words, we have proved that this would be equal to 1 plus 2 plus 3 all the way to n squared. And so if you want to answer the initial question of chessboard, that would basically be equal to 1 plus 2 plus 3 plus all the way to 8 squared, which turns out to be 1296, and we have our answer. So above I sort of took just one example, and then I didn't generalize it, although I should have, that if you have any m by n and then you're looking at m by n minus 1, you will have twice of those. For m by m minus 2 you will have thrice of those, and so on. But you get the point. And so we have reached at our answer, but there's one very much cooler way of doing this, and it's by a combinatorics. So if you have any n by n, right, we can notice that there are n plus 1 vertical lines and n plus 1 horizontal lines. And so what we can observe is that any rectangle will basically be just a combination of the line that you choose, the vertical line that you choose, and the horizontal line that you choose. Let's say if I number these 1 2 3 and 1 2 3, let's say I choose these two and these two, it would basically give me this rectangle. What we need to find is how many different combinations of these vertical lines and horizontal lines there can be. In other words, we just need to find n plus 1 combination 2 and multiply it with n plus 1 combination 2, and so this would basically be nc2 multiplied with nc2 in our case, and this is the same as 1296. And so, well, one thing is that this is actually the same formula, because n plus 1 choose 2 would basically be n plus 1 multiplied with n over 2, and then you multiply it with the same thing. In other words, you square this, and you have the same answer, right? And in fact, this is much powerful, because it we can see that if we have any m by n instead of a square, we have a rectangle, then the total number of rectangles will be m plus 1 choose 2 multiplied with n plus 1 choose 2, and we are easily done. QED.